Last week we had some problems on, it was called derivative shortcut to tangent line. So this is kind of the beginnings of us putting stuff together, all the stuff that we found out with the problem that we're interested in. We're interested in finding the equation of a line tangent to a curve at a given point. Started off the slope of the line, but then we want the equation of the line. So the idea is that we want to find the equation of the line tangent to some function f of x at some point, at a given point. So here is the general form of the problem. What we need to do is, this problem comes down to find the equation of a line. To find the equation of a line, we need two things: a point and a slope, a place to start and a direction to go. This is why we like lines. They are super simple. There's a place to start and a direction to go. So find the equation of a line involves two things. We need a point, x naught, y naught, and a slope, m. And we could also find, if we have a point where x naught is 0, then we'll have 0b, so the y-intercept. But in general, we'll have a point x naught, y naught, and a slope m. Once we have a point x naught, y naught, and a slope m, we can put those two things together into the point slope equation of a line. So y starts off at y naught, and we add, I spelled add wrong. Plus is the little T shape, not that double L on its side. Once we have those parts, x naught, y naught, and slope, then we can just put them together into our point slope equation of a line. Y equals y naught plus m times x minus x naught. The generic statement of the problem has half of a given point. It gives you the x coordinate of the point. So x equals x naught. We need to figure out what y naught is. So the x naught is the given part. We need to plug in to find out the y naught. So x naught is half the given point. So when I say find the equation of a line tangent to a function at a given point, usually the setup of the problem is I give you half the point. The point is x naught and y naught. X naught is given. To find y naught, we just plug our given coordinate into the function. So to finish this part out, y naught is f at x naught. Now we have the whole point for the equation of a line, not the point of the problem. The other thing that we need for the equation of a line is the slope of the line. And since this is a tangent problem, that means derivative. Tangent, rate of change, slope of the tangent, rate of change, derivative, all go together. So the other part of the problem, since we're looking for a tangent line, the slope will be the derivative evaluated at x naught. This is the new thing that we're doing since we're in calculus. We found equations of lines in the past. Now we're putting together that with that new idea, find the derivative, plug in the point. So when I say f prime and x naught, we find the derivative first, then plug in x naught. If we just plug in x naught, we'll have a constant, the derivative will be 0. and all lines will be flat. So for this, we find the derivative. We'll find the derivative using nx to the n minus one, and then we'll plug in the x naught. So for example, I didn't call this f of x. So in this problem, I wanted the slope of the line tangent to the curve square root of x at the point where x is equal to 4. So the 4 is your x naught. We want to find a point, so we'll plug 4 into the function. So x naught is 4. Y naught will be p of 4. Square root of 4 is 2. So our point is 4, 2. Half the stuff we need for our tangent line. Since we're finding the equation of a tangent line, we'll take the derivative. We have a square root of x, which we're going to read as x to the 1/2 power. Then we'll find the derivative by doing n x to the n minus 1. So we get 1/2 x to the minus 1/2. To find the slope, we plug in the point that we care about. So 1/2 times 4 to the negative 1/2. If we want to look at that 4 to the negative 1/2, the negative is going to take the 4, the exponent. A negative exponent will be positive in the denominator. And the 1/2 power is a square root. So 4 to the negative 1/2 will be 1 over the square root of 4, which is a half times another half is a 4. So now we have the slope. So now we have a point and a slope. We have all the pieces that we need to put together our equation. So point slope form of a line, y equals y naught plus m times x minus x naught So if we were just going to be writing this as an answer on a piece of paper and then handing it to me, this is how we could write it. Since we're just writing things, we have the freedom to write our nice vertical fractions. That vertical fraction in front of parentheses. It makes it very clear that the 1/4 is being multiplied by the x minus 4. If we were going to type this, if we had to say type this into Canvas, like some of you did over the weekend, if we're going to type this into Canvas, that 1/4 is acting like a fraction, and it is a coefficient. It's not acting like it is those things. That 1/4 is a fraction and a coefficient, so we'll want to put it in parentheses. So on single line syntax, I might write y equals 2 plus 1/4 in parentheses, and then x minus 4. It would mean the same without the parentheses around the 1/4 to anyone that offers a strict reading of PEMDAS. 1 gets divided by 4, the result is multiplied by the difference of x and 4. But some people will just read 1 divided by, and then put that product all in the denominator. Since we don't want that to happen, we put parentheses around the 1/4, and our communication is now unmistakable. We want to make sure that we have nice, clear communication. Any questions? How's everybody okay? This is one of the nice things about math. There is a way to write things precisely. This is one of the annoying things about math. There is a way to write things precisely. This is what the legal system is trying to do. This is what laws are trying to be. Law is just trying to be like math. It fails horribly. Law tries so hard to be like math. The structure of math, the way that we think about math, is we take some things that we all just accept, right? They aren't theorems. These are just true. Sometimes it's shit that we can't even prove, right? But if we go back to Euclid, way back in the day, there were 5 postulates. It's like, oh, these are 5 postulates. This is the shit that has to be true. And everybody looks at it and it's like, oh, yep, that is just true. Except the 5th, the parallel postulate. Euclid and everybody else is like, oh, what about this one? And Euclid's like, oh, quiet, we're gonna make some geometry. Well, you don't really need that 5th one. For the geometry that we're gonna be making, parallel postulate. And he's like, all right. So from those 5 postulates, all of the theorems in your geometry class are derived and then proven, just using those things. Once you get a theorem and it's proved, then you get to use that theorem to prove other theorems, right? That's how it is. And that is the structure of the law. That is what the law is trying to do. We hold these truths to be self-evident, and then it lists those things. It's like, oh, this is what we're basing this on. And then we try to derive everything from that. It's like, well, if those things are true, then these are the laws that should apply. It's trying so hard to be math, but it's failing because it doesn't have a precise language. It's got fucking English. Fuck. What a disaster of a language. I'm not picking on English in particular. Every spoken language is the same way. Because language evolves and certain things just start meaning other things. And so we have to change and come up with new words. You know what I mean? How's everybody okay? Not with language changing. That's kind of a pain in the ass. It's not supposed to happen so fast, but we're kind of communicating a lot faster than we used to. So it evolves very quickly. How's everybody okay? So this on Friday, this was our first encounter with the kind of the prototype problem that we're going to be looking at. There's all kinds of things that we need to add to this. Like we need more than just this one derivative shortcut. We need to be able to find the derivatives of other functions that don't look like x to the n. We need to have a better understanding of what slope represents, more examples of rates of change and instantaneous rates of change. We need to make things rigorous with limits. Because we're trying to we express the derivative as a limit, and then I immediately glossed over that. It's like, oh, yeah. This is how you do it, nx to the n minus one. Just gonna do that. And everybody looked up the algebra that was involved in using the definition of a limit with all definition of the derivative with all the limits and stuff. And like, oh, yeah, we will nx to the n minus one. We are all down with that. That is okay. Any questions? Comments? Smile remarks? How's everybody okay? We have a nice weekend. I, in fact, did not watch the football game. Yeah. I have not watched the football game in a very long time. I stopped watching baseball in 2009. Not for any reason, nothing specifically happened. But then in 2010, I had to stop. I didn't watch baseball, and I could never watch baseball again. This is because I'm a Giants fan, and I'm a baseball fan. And it's because I didn't watch baseball in 2010, they won the World Series. We ignore 2011, but I also did not watch baseball in 2012. And what happened? They won the World Series again. Now, once again, we ignore 2013 because this is how patterns work. Ignore that part. But what happened in 2014? Shit, I can never watch baseball again. Ever. Which means I'm horribly out of touch. So I heard about all the rules changes and stuff like that in baseball. And I had to text my friends, like, oh, dude, when did this fucking happen? It's like, well, were you under a rock? I'm like, oh, shut up about my rock and my living situation. How's everybody okay? I used to be like hyper traditionalist about baseball. It was I look back at the way I was a baseball fan, like in like the late 80s, early 90s, and I'm like, gross. Those were terrible takes, Leach. What the fuck was wrong with you? Anyway. Modern take. I'm 100% on board with, people using steroids. Fucking get that bag. Okay, this is why I think we all need to pull our collective underwear out of our collective butts. We let Shaquille O'Neal play basketball. And you're telling me that we're worried about being fair? No. No. If we're going to let literal giants play basketball, where being a giant is a gigantic advantage, I don't think we get to play like the fair card. We let Michael Phelps swim. Dude is a fucking mutant. And his mutant power specifically makes him a better swimmer. No. If we're gonna let that dude swim and Shaquille O'Neal play basketball, no shade to Shaquille O'Neal. I mean, I think he's cool. That's fine. But no, we're really not worried about fair. What's most embarrassing is the people that didn't think that that was going on. I don't know if you saw Mark McGwire at the beginning of his career. He was like regular size. He wasn't, and then like a couple years later, his hat size got bigger. Barry Bonds, your hat size got bigger. If your hat size be getting bigger, you're wrong. Everybody knows. So no, I'm not doing that. Come on now. I think it's embarrassing that we all gave a crap, but I actually don't like that style of baseball. Hit ball, go far. Ball, go far. Yay! Right? I don't really care for that, but that's what it was. Everybody knows. Like in the late 60s, where you could lead the league in hitting with like a 300 batting average. because the mound was like 8 feet off the ground and you were like throwing the ball directly down at the batter. He's like, right? And furthermore, I think they soak the balls in water before they throw them so you can hit them. And it was like a boom. What are we talking about? Oh yeah, I got this right. Sorry. So this was the problem that you had. It showed up on the canvas and you'll want to type it in that way. I suppose I just wrote the answer, but if you're just going to copy down the answers, then I'm not going to be helping you anyway. You're not looking to learn stuff, you're just looking to pass. And I can't fix that. That's a you problem. All right. So if you would recall, if I could get my shit back on track, it's Monday. Limit. There's a lot of stuff going on with limits. There's a lot of stuff going on with limits. We talked about the definition of a limit for every epsilon greater than 0, or sorry, beginning. Limit as x approaches c of f of x equals L, if and only if for every epsilon greater than 0, there's a delta greater than 0, such that the absolute value of x minus c less than delta implies the absolute value of f of x minus L is less than epsilon. There's a lot of things that are going on in this definition. There's one, the rigorous definition of what it means. That's the epsilon delta stuff. So there's a lot of stuff going on here. There's how we define it, so it has some kind of rigorous meaning. There's also our intuitive understanding of what we're talking about. We also have to develop an intuition. We also have to have an intuition about how how this works. Then we have to have kind of a practical working knowledge. And we have to have some kind of practical stuff, some mechanics. We have to have all of these things. They all go together into what we combine. It's a package of understanding limits. I have kind of a generic understanding about how electricity works. Kind of generic understanding about how electricity works. I will 100% not be rewiring my house because I would, what's the word? Be dead. I would definitely blow myself up. I know enough to be like, oh, that seems like a bad idea. Let's just I need more plugs. So I'll just take one power strip and plug it into another power strip. Intuition, based on what little I know of the theories, my intuition is like, oh, that seems like a bad idea. So we talked about the definition. That's the part with the epsilons and the deltas. Our intuition about limits, that's kind of describing what's going on with the epsilons and deltas. That's where we say, we can make f of x as close as we like to L, and f of x as close as we like to L, we can get f of x within epsilon of L for any epsilon, so long as x is sufficiently close to C. F of x as close as we like to L. That's within epsilon of L, the absolute value of f of x minus L less than epsilon, so long as x is sufficiently close to C. That's the delta part. Absolute x minus C less than delta. We start with the epsilon as our tolerance, and we figure out if there is some delta which will make this happen. If there's some delta that will make this happen. Another idea about that's more practical about our intuition is like, oh, where is the function heading? If you are driving south on I-5 in California, you are headed towards Los Angeles. If the aliens invade and for some reason blow up Los Angeles and Los Angeles is no longer there, the limit of your function is still Los Angeles. It's just that when you get there, there'll be a big old crater and some aliens going, ha, make some movies now. And then we'd be like, oh, but we were going to make movies about you. And then they're like, oh, shit, we shouldn't have blown up Los Angeles. So we're thinking about where the function is headed. We want to be able to picture this, and we want to see where this is going in the numbers. We've already done that part. So here's a graph of function. Here's the graph of a function. And we can see 3 places where there's something fishy going on in the function. Let's put some Y scale on this. So we want to think about what the limit is at each of these points, if the limit exists. Now at x1, we could say the limit as x approaches x1. We're asking the question, we're thinking to ourselves, where is the function headed as we move towards x1? As we move towards x1 from the left, we see that we're headed towards 5. As we move towards x1 from the right, we see that we are headed towards 5. From both sides, we're headed to the same 5. So we could say that the limit as x approaches x1 of f of x is equal to 5. From the left and the right, the function is headed towards 5. That's the practical part of it. From the left and the right, the function is headed towards 5. From both sides, f of x is headed towards 5. What's actually happening at 5 is not the concern of the limit. The limit does not care that f of x1 is 15. What's actually happening at 5, not relevant. The limit doesn't care what's actually happening at 5. Oops, not at 5, at x1. We're not worried about what's going on at x1. We're worried about what happens as we approach x1. In this case, f of x1 is equal to 15. That's what's happening at x1. But as we approach x1, we're headed towards 5. F of x1 is equal to 15. Where we're headed and the actual value being different feels unexpected. It's like, oh, we're headed towards 5. Oh, but no, the butler did it, right? That seems out of nowhere. So we would say that f of x is discontinuous when x at x1. So because where we're headed and where the function actually is at x1 are different, we would say that the function is discontinuous at x1. The fact that where the limit, what the limit at x1, limit approaching x1, and the value at x1 are not the same. Then we would say that f is discontinuous at x. Looking at the next point, x2. As f approaches x2 from the left, we're headed towards 10. As f approaches x2 from the right, we're headed towards 5. We are not headed towards some one value. The function is headed towards different places. So we'd say the limit as x approaches x2 of f of x does not exist. F of x is headed towards different values from either side of x2. If we approach from the left, the limit is 10. If we approach from the right, the limit is 5. We have a notation for this because this is math class, and of course we have a fucking notation for it. When we want to say that the limit as x approaches x2 from the left, we make a superscript of a minus. That superscript minus means from the left. So we would say the limit as x approaches x2, if we put a minus up there, that's us saying the limit as x approaches x2 from the left. Looks like I'm just making a fancy x. So that superscript on the x2 means we're approaching x2 from the left. The superscript minus. The superscript minus means that on the x2 means that x is approaching x2 from the left. This is a one-sided limit. Similarly, we can approach x2 from the right, in which case we'll put a superscript of plus. As we approach x2, as x approaches x2 from the right, the function is headed towards the value 5. Since these two limits, these two one-sided limits are not equal, we say the limit does not exist. Our two one-sided limits are not equal, so our limit does not exist. Questions? In this case, we would also say that f is discontinuous at 2. because the limit doesn't exist. All right, that's gonna do it for today. Make sure you jump on to the Canvas and do the different derivative shortcuts to find the equation of the tangent lines. If you did not get your equation of derivative shortcut 2 back, please come and see me. I have them up here. That's it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.